receiving this both in voice as well as in text chat. Let me know if there's any technical problems. Okay, so it's been some years since I've done this at VWBPE. I'm really glad that the conference has been able to be sustained for so many years, and I'm very happy and privileged to be here today with you. So today I'm sharing a learning intervention which my team and I enacted in collaboration with the National Ping Tung University, which is in Taiwan. So my team and I are originally from Singapore. We had this collaboration with our Taiwanese colleagues. Okay, so here we go. In text chat, you would see that the intervention was carried out in an undergraduate chemistry course. So earlier, in the few minutes before today, one of the questions was, is today's talk on chemistry? I'm using chemistry as an example, but natively, I am not a chemistry educator. So natively, I am a curriculum designer from the Ministry of Education in Singapore. So we could always talk about other applications of the approach. Okay, here goes the next. So as I said earlier, my team and I are from the National Institute of Education in Singapore, and we did not explicitly set out to design a learning unit in chemistry when we were thinking about how to use augmented reality. Rather, we were more interested in thinking about the affordances and disaffordances for learning of the current state of augmented reality, which for the rest of the session I will refer to as AR. So importantly, we were interested in what AR is good for or might be good for in terms of learning and learning design, and what might it not be so good for. Okay, here goes the next one. I'll advance the slides later, okay? I have some slides, as you can see, but this is all just contextualization first. So, although AR is relatively new, it has been used in learning, training, and education in various contexts, as I'm sure everyone present here already knows, because by definition, we do operate in this space, or at least have some interest in this space. Yes, that's right. The slides will be advanced once we get past the contextual information. So as I said, thanks, Laurie. So although AR is new, it has been used in various contexts in learning. However, in general, despite the variety of contextual uses, for example, as outdoor learning trails, as visualization for mathematics, and so on, the design paradigm undergirding these present uses is more or less the same. That is from our point of view, at least. So we see, despite the diversity of disciplinary applications of AR so far, we see a common design paradigm. And the common design paradigm that we see, if we distill it into its most generalized form, is that AR is used to exemplify the concept in question. And this concept can be respective to the various disciplinary domains. So, for example, in geography, it might be AR might be used to exemplify or to illustrate ecosystemic interactions, or in mathematics, AR might be used to help learners visualize topology, and so on. So basically, AR is used to help the learners visualize by giving them exemplars of the concept. Yep, so basically I just said that. In other words, the foundational assumption behind the use of AR in learning so far has been that by affording learners opportunities to interact with three-dimensional renditions of the concept in question, By affording learners opportunities to interact with three-dimensional renditions of the concept in question, the learners will come away with a clearer understanding. So, by giving them opportunities to observe, interact, zoom in and zoom out, whatever the disciplinary concept, the assumption is, to use the American phrase, the learners will somehow grok the concept. So this design paradigm is expensive and not very scalable. Why? Because someone needs to be there to design the exemplar in the first place, and from a curriculum point of view, every time the syllabus changes, the exemplar may or may not need to be changed accordingly. It is also not very scalable because of the cost of involved in making the example an exemplar. So our team was interested to try to approach the use of AR in learning from a different perspective. We were interested to investigate the extent that AR could be used as, instead of exemplars, as canvases of learner expression. So that's one key operative word for this afternoon's presentation: canvas. We were interested in this perspective because over the past 10 years, we've kind of had some experience in helping teachers from Singapore and the region design curricula in which the intuitions of novices is surfaced for subsequent dialogue among peers and their teachers. While we focus on intuition, let me just have a quick look to see whether we are going. I don't think, we're not going into the background of why we are focusing on intuition because that's a totally separate topic, but you can have a look at my Google site if you're interested. Fundamentally, we're interested in intuition because many curriculum frameworks focus on surfacing learner misconceptions, but we see intuitions as undergirding the misconceptions. So we call this approach to curriculum design disciplinary intuitions. Right. So it occurred to us that since we were thinking about using AR as canvases, or what we call learner-generated augmentation, using AR as canvases for learners to express their naive and evolving understandings, chemistry might be a suitable disciplinary domain in which to design a learning unit. This is because in both inorganic as well as organic chemistry, a key concept to be understood is the three-dimensional forms of molecular structures. These structures are, of course, invisible to the naked eye. Okay, so let's advance to the first slide. Okay, so let's see. Over the decades, chemistry educators have devised several ways to help novices bridge this gap in understanding. What gap in understanding are we referring to? The gap in understanding of understanding three-dimensional forms, which are generally invisible to the human eye. So examples of such ways would include using physical models resembling balls and sticks to digital visualizations. This is what you see on so the ball and stick is coming up next, as you can see, since there's a preview slide there. Okay, so I'll just click on it since I'm talking about balls and sticks. Yep. Okay, next. Yep. Excuse me. In parallel with this, another critical factor for chemistry educators to consider is how to help learners mediate their transposition from 3 dimensions into 2 dimensions. And more than that, 3-dimensional tangible artifacts such as models and manipulables to 2-dimensional abstractions and notations. Why 2-dimensional? because ultimately, when two chemists or two chemistry educators talk to each other from different backgrounds and narratives, it's the same with any of your own native subjects. For example, for music, if you have a musician from Germany talking to a musician from Japan, the language that would bridge the cultural gap would be, of course, the language of musical notation, apart from others. And likewise, say in geography, the language would be the language of maps. So in chemistry, it's the language of molecular representation. And this applies to any of the major disciplinary domains. In the case of chemistry, it's a little bit more complicated because the chemical notation is, of course, in 2 dimensions, whereas the actual physical artifact is in 3 dimensions. What did I just do? Let's see. So it was from this background that my team and I approached our friends from Taiwan to see if they would be interested in enacting a learning unit among their undergraduates. Okay, which used AR as canvases for the students to express their nascent understandings about organic molecular structures. So we carried out the intervention in the summer of 2018, last year, using a freely available and cross-platform app which can be downloaded to any smartphone or tablet that supports AR. Okay, so the app is Just Align from Google. You can have a look. You can Google Google's Just Align. So to take us on a small tangent, because after all this is VWBPE and VW stands for Virtual Worlds. Virtual worlds and immersive environments such as Second Life and OpenSim have long, as you know, afforded us the ability to res prims. Everybody present in this room, in this space, knows that. So resing a prim is essentially creating something from no raw materials, which has always been the big draw of Second Life and OpenSim. It is this foundational affordance to res prims that makes worlds and environments such as Second Life and OpenSim so potentially powerful for learning as well as fun. It is also because in real life, we are unable to create something from nothing. So the act of creation is fundamentally empowering, especially in the context of learning. So to close the tangent, the Just Align app affords us the ability to res sketches like so, without the need to go in world. So here what you can see is a picture of one of my interns using Just Align to augment the I think it is I'm not a physicist, but it's a battery thing. And he's doing, I believe it's Fleming's right-hand rule or Fleming's left-hand rule, representing the current flow as it should be in terms of the circuit. So this would be an example of how the application of how the curriculum paradigm might be applied to something other than chemistry. Hello, Alex. Thank you for being here today. I'm very grateful to see so many of you. So just as in Second Life, the resing is done in a way congruent with embodied cognition through the extended arm, this time by using the finger to sketch on the screen. So it's just as if we were resing something. Okay. Okay, currently, as AR standards are new and still evolving, sketches do not persist once the app is closed. So, for example, I guess I'll show you this one, the next slide. So this is a screenshot from the actual intervention itself. That's why the background is so messy. And the task was here for the students, for the undergrads, to render or to represent their understanding of a rather complex molecular structure in organic chemistry. So currently, sketches do not persist. Okay, we know that, of course, in SL and in OpenSim, our prims do persist. So I hope this is likely to change in the future, which is not too long from now, as Apple, Google, and Facebook have all expressed keen interest in developing AR standards. Even though they do not persist, Just Align, the app from Google, which is free, affords, oh, by the way, I do not represent Google. I have no vested interest in Google. Just Align affords two key features which are very useful to educators. And what are these two key features? Namely, the ability for a group of learners to collaborate on a common sketch, similar to how we would, for example, build something in Second Life or OpenSim. And second, the ability to record the sketches in real time for subsequent playback and review. Again, to use the analog, the metaphor from OpenSim and Second Life, is just as if we would be recording our collaborative print building in real time using some kind of screen capture software. So for the intervention in Taiwan, 36 third-year undergrads took part. And I'm not sure how many chemistry educators there are among you in the audience right now. I don't think there are that many. So I will not go into the details. If you would like the details, I can refer you to the paper that we recently published. Okay. Oh, no, are you a chemistry educator? Oh, I see. Oh, wow. Okay then. So, in a nutshell, they were asked to sketch molecules of ammonia, glucose, and an amino acid. I'm not sure which one, using the AR app. The methodology is detailed in the paper. A total of 80 sketches resulted, and they were coded according to accuracy. So the coding was proprietary, simply because this kind of design approach has not been done before. So we came up with our own coding scheme. The AR-based sketches were also compared with paper-based sketches drawn after the intervention by the same students. So yeah, our collaborators in Taiwan are chemistry educators. And what happened was they reported that the intervention helped them have a clearer understanding of so they reported that the intervention helped their students have a clearer, They reported that the intervention helped them have a clearer understanding of specific misconceptions that individual students had with respect to understanding molecular structure. That is a very long sentence. Basically, I'll try to break it down in subsequent here. Okay, so I think this is important. This was especially so in the case of students who could sketch accurately on paper but had difficulty expressing their rote memorization as a three-dimensional sketch. Okay, I'll say this again. The chem educators found it useful because like good East Asian students, sorry to fall into stereotype, but like good East Asian students, the students knew how to do things when asked to do so on paper. But when pressed by questioning and interrogation, they revealed that their understanding was not strong because they did not have foundational, their foundations were not strong. They knew how to write to the test, but when there was a twist in the question, they would not. So basically, they would fumble. So basically, what we were interested in doing is to try to intervene at an early level to flag these gaps in understanding, so that so that it will be more explicit for their teachers. Okay, so this is what I mean when I say they reported that the intervention helped them have a clearer understanding of specific misconceptions that the students had, especially when the students could accurately sketch on paper but had difficulty expressing their rote memorization as a three-dimensional sketch. Yes, my point, our point, one of the points, a small amount away from my mouth. Okay, thanks, James. Got it. Sorry, I can't, yeah, I wasn't aware I'm turning red. Okay, keep giving me feedback, James, thanks. Yeah, so as you said, that problem is common, and not only in Chem, I'm sure, but in other subjects. Like for my own native subject, geography, they can memorize things like for example, the shapes of different geomorphological features such as plateaus and ridges as represented by contour lines. But when you actually get them to try to explain why contour lines mean certain things like concave slopes and convex slopes, they kind of break down in their explication. So yeah, so Jazz, that's what I'm trying to say, in the sense that maybe it helped them not so much better understand what they had memorized, but it helped their teachers better understand why what they had memorized did not sometimes match what how they tried to explain it. Yeah, I'll say that again. It helped their teachers understand why what they memorized did not sometimes match how they tried to explain it. So, in other words, in the written test they would do well, but in the tutorials they would not. Because in the tutorials they had the space to be questioned in detail. Whereas in the written test, generally speaking, as you know, East Asian students kind of, they kind of are able to do the test, which is a problem if you're a teacher. A little further from my mouth. Okay. So James, okay, I'm still too close, right? Okay, no problem. Actually, it is a problem because I'm short-sighted, so I'm okay, but never mind, too much information. So, yep. Yes, that's right, Jess. Yep, you got the point. So I'll go on with your permission. So, learner-generated augmentation, which is the approach that we are terming, therefore describes the affordance of augmented reality for learners to sketch in 3 dimensions using just their finger. Such an affordance has never before been possible. In summary, have I reached the end of my talk? I'm near the end of my talk. In summary, almost all major technology companies are in the midst of concerted pushes into developing AR. Okay, there's a reason I'm saying this. Apple is no exception. I'm not trying to promote Apple. I'm trying to turn Apple upside down. So at the time of writing, one of the blurbs on its website read, this is what it read. This is from Apple. So Apple says, first-hand experience is one of the most powerful ways to learn. And with augmented reality, you can experience just about anything you can imagine. Break down the complicated mechanics of a car engine before touching a spanner. Or analyze the most minute bones of the human body without making a single incision. The possibilities for learning are endless. Count the number of cliches. So these statements are factually true and cannot really be disputed. However, what this sharing has attempted to do is to encourage teachers, school leaders, curriculum designers such as yourselves to approach the question of augmented reality in education from a diametrically opposed yet complementary perspective. So we are trying to upset the apple cart. How? That perspective is best described in reversing the sequence of words in Apple's blurb, such that it reads, first-hand experience is one of the most powerful ways to learn, and with augmented reality you can imagine just about anything you can experience. Have I got it right? Yeah, I have right, I hope. Yeah, okay, I think that's the end of that. Okay, I encourage you to try to approach your own respective disciplinary domain from this perspective and see if such approaches might lend themselves to helping you surface novice intuition with AR through learner-generated augmentation. So just to give you a few slides, since I've obviously finished my text, so I'll just go through the remaining slides. So here what is being drawn is a molecule of, I think it's ethane, I can't remember, CH4. CH4 is ethane, I think, or is it methane? Methane, thanks. So here apparently what the problem was that the candidate did try to draw everything on the same horizontal plane. So the pictures are taking a little bit of time to res, and this is not working very well. But essentially, and this is actually all in the paper. Not that I'm trying to refer it. Here we are. So this one was turned around, right? But you can see that the molecule, the angles in the, I'm not using the correct word because I'm not a chemistry person. But they are all like flat and two-dimensional, which reflects two-dimensional thinking. Those of us who saw Star Trek: The Wrath of Khan would. Okay, so basically, no matter how he turns around, it's still a two-dimensional representation, which is not right. Okay, so anything else interesting? There's one more example. Oh. So moving from behaviorism to constructivism. Yes, yeah, you could say that, Edith, or Edith. In the sense that the behaviorism, as I think you understand it, would be the outward behavior. In other words, the writing to the test. That's the outward manifestation to constructivism. So this was the example of the. You see, remember earlier we had this little conversation about how he can. How he can draw the correct thing. So this sketch is drawn by the same candidate who drew this thing, which was, so in other words, he knew how to represent it technically, but his correct representation did not necessarily mean that he understood what he was drawing, and this is a big problem. Especially with East Asian students, because we are very good at rote memorization. Okay, so don't worry, I don't have a whole lot of slides. I was quite sparse with the slides. Okay. Anything else? Okay, so this second set of slides, remember I talked to you about the coding, right? About how the examples were coded. So this one is actually annotated by one of my interns who does have formal chemistry training, so we just need to wait for the thing to res. Here we go. So what does it say? Depiction of what? Depiction of ammonia with extra H atom. Okay, so 3D depiction of, oh wow, I have no idea how to read that. And then the last one, I believe, is, okay, but I guess you get it, no, we must wait for the last one. And then the final slide is the list of, devices which are compatible with Just Align, so you can try it out yourselves with your own respective domains. So, here we go. So H atom attached to the central carbon atom on a separate axis, and so on and so forth. It's all in the paper if you're interested. Okay, so I think everybody should be interested in this slide, which is the list of compatible devices. Of course, this is like the bare minimum. The more up-to-date your device, the more sophisticated and easier the AR processing would be. Okay, So yeah, that's half an hour. Good. So we have good amount of time for questions and discussion. So thanks everyone. Yep.